Welcome to the Explainer. Today we're taking on a genuinely fascinating mission, demystifying exactly how large language models actually work. For a technology that has literally revolutionized how we interact with machines, the core mechanics, well, they're often shrouded in this kind of digital mysticism. But today we're going to peel back those incredibly complex, billion-parameter layers to reveal the surprisingly simple, elegant mechanics running underneath the whole shebang. Our goal? To give you a clear, easy-to-grasp executive summary of the computational mind.
Okay, let's dive into this roadmap. First up, adding one word at a time. Then, inside the neural network. Third is training and human feedback. Fourth, the secret structure of language. And finally, unlocking computational superpowers.
Part 1. Adding one word at a time.
To break down this grand illusion of artificial thought into its absolute most basic mechanical function, we really have to ask the multi-billion-dollar question, right? What is ChatGPT actually doing when you give it a prompt? I mean, when you see these paragraphs of highly structured text just flowing onto your screen, it feels like the system is thinking. It feels like it's deep in thought, pondering your question and crafting this comprehensive essay from scratch. But the real answer to this fundamental question is remarkably, almost shockingly simple.
Now, what's really interesting about this is that the core trick of the trade is fundamentally just guessing a reasonable continuation of text. It's essentially asking itself over and over again, okay, given the text so far, what should the very next word be? And it does this by picking from a ranked list of probabilities, which it figured out after scanning billions of pages of human-written text. So it's basically a highly advanced autocomplete, just choosing the next most logical piece of the puzzle based on vast statistical experience.
But here's where a little bit of algorithmic voodoo comes into play, something often called the temperature. Think about it. If the model rigidly picked the absolute highest probability word every single time, the text would be incredibly flat, repetitive, boring. It just wouldn't sound human. So to get that flowing, creative, human-like response, the system has to occasionally be allowed to pick lower-ranked words at random. Injecting that tiny bit of unpredictability, that is exactly what introduces the spark of creativity.
Moving on to Part 2. Inside the neural network.
Stepping into the actual machinery of meaning, the absolute first thing to understand is that the AI doesn't read words the way you or I do. It processes what are called tokens. Now, a token is just a convenient linguistic unit. Sometimes it's a whole word, sure, but a lot of times it's just a chunk of a word, like the prefix pre or the suffix ing. And this brilliant little abstraction is exactly how the model handles complex compound words, rare terms, and, yeah, occasionally how it accidentally invents completely new hallucinated words.
Once the text is chopped up into these tokens, they get converted into embeddings. You can think of an embedding as a massive array of numbers that represents a sequence of tokens in this vast, high-dimensional semantic space. This right here is where language becomes pure mathematics. By turning tokens into these huge arrays of numbers, the neural network can actually map out which words share similar meanings and contexts, grouping them together spatially inside its digital brain. It's wild.
And to really understand how it processes those embeddings, we have to wrap our heads around the sheer, mind-boggling scale of this architecture. 175 billion. That number represents the individual weights inside a model like GPT-3. 175 billion. Every single time the system wants to generate just one single token, it relies on this colossal web of parameters to weigh the mathematical context and predict what comes next.
And this brilliantly illustrates the three actual operational steps. Number 1, convert your input tokens into those mathematical embeddings. Number 2, let those numbers ripple forward through the successive layers of the neural network. And number 3, produce a new output token. Notice something? There's no looping back, there's no internal pondering or rereading. The data simply feeds cleanly and directly forward through the network, running this exact same sequence over and over for every single new word it generates.
Part 3. Training and human feedback.
So, if the network is literally just predicting the next token using billions of weights, how do we teach this massive web of numbers to behave like a helpful conversational assistant instead of just some chaotic text generator? Well, it comes down to some vital, distinct training phases. First, the model passively reads billions of pages of web text just to learn the statistical patterns of language. But, that alone just makes a parrot. The absolutely crucial step is human feedback. Humans actively interact with the model and rate its responses. Then, the neural network is explicitly tuned to predict and optimize for those human ratings. This fine-tuning is exactly what transforms a raw statistical engine into a well-behaved, useful chatbot.
And what's genuinely amazing about this architecture is its surprising efficiency after it's been trained. You might think, oh, I need to go into the code and algorithmically adjust billions of weights to teach it something new, right? But it doesn't need algorithmic retraining to learn a new behavior on the fly. Simply giving it one well-crafted prompt successfully redirects the network's output trajectory. You literally tell it once, and it immediately uses that context to generate the next sequence of text.
Section 4. The secret structure of language.
By analyzing how this technology actually works, researchers have uncovered a rather profound, almost philosophical breakthrough hidden inside the math. The core realization here is that language is, at a fundamental level, somehow simpler than it seems. I mean, we've always viewed human language and the human thinking behind it as something infinitely complex. But the very fact that a neural network with a relatively straightforward structure can produce such incredibly human-like text, well, it suggests something incredible. It suggests that human language actually follows a much simpler, more law-like semantic grammar than we ever previously assumed. And this AI, it implicitly discovered it.
Let's move to and see how this builds into Part 5, Unlocking Computational Superpowers.
To see the future here, we really have to contrast two very different paradigms. On one side, we have statistical AI, like ChatGPT. It generates highly plausible linguistic patterns based on what it's read. It weaves together the statistics of conventional wisdom, meaning it sounds right, but it doesn't compute true facts. On the exact opposite side, we have symbolic AI, like computation engines such as Wolfram Alpha. These systems don't guess. They compute precise, formal mathematical facts. Now, they don't have a natural conversational flow, but they are perfectly mathematically accurate. Take a look at how these contrast in practice. The statistical model gives you an uncomputed conversational approximation of, say, the flight distance between Chicago and Tokyo, just based on text it's seen before. But the symbolic approach provides the exact computed miles based on actual data. Relying entirely on a model that just guesses the next word definitely has its limits when you need definitive truth. We clearly, absolutely need both.
So, the crucial point is this. The true superpower lies in combining these two approaches. By using the natural language interface of a statistical model to understand exactly what you're asking, it can then be programmed to trigger precise formal computation engines in the background. This allows the AI to speak in fluid, natural human language while pulling its facts from a perfectly accurate structured knowledge base. That right there is how we grant artificial intelligence true computational knowledge superpowers.
As we wrap up this explainer, I want to leave you with a final, rather provocative thought. If a neural network can so effectively, mathematically map the structure of human language, and by extension, the logic of our expressions, just by guessing the next word, what other irreducible complexities of human thought are we about to uncover next? The computational mind is really just beginning to wake up, and the implications for science, philosophy, and technology are absolutely boundless. Keep learning, keep questioning, and thank you so much for joining me for this executive summary.